Shown in the figure below is an RL circuit powered by an AC source. The resistor has a value of 4,000 ohms. The inductor has a value of 2 millihenries. The AC source has a frequency of 183 kilohertz and a peak voltage of 10 volts. You might be surprised by the number of significant digits in the frequency, and you could guess that this problem was rigged in order to make the results turn out to be particularly even numbers. This is certainly true because the purpose of this problem is to gain a better understanding of the quantity phase. The problem begins with a set of calculations that should by now be quite familiar, and that is we'll calculate the total impedance as well as its phase angle. We do so by making a vector diagram and recognize that the vector sum of the impedances of the resistor and the inductor gives us the total impedance of the circuit as well as the phase. We can take a moment to plug in 2 pi times the frequency times the inductance, and we'll get a total of 2,309.0 ohms. This means that the magnitude of the impedance of our circuit will turn out to be 4,618.6 ohms. Furthermore, the phase of the impedance will be the inverse tangent of the opposite over adjacent side, and plugging in the numbers, we get the very round result 30.0 degrees. For our second calculation, we are to determine the magnitude of the total current expressed as a peak value through the circuit. The total current is total voltage over total impedance, and this implies that the magnitude of the total current is the ratio of the two magnitudes. The prior formula is true in both peak and RMS format, and so we're able to calculate the peak value rather quickly, and the peak current turns out to be just over 2 milliamps. The phase of the total current will be equal to the difference in phase between the total voltage and the phase of the impedance. By convention, we take the phase of the power supply voltage to be 0, and as a result, the phase of the current will be negative 30 degrees. Our final calculation before we begin the important new consideration regarding phase is to learn the magnitude and phase of the peak voltage on the inductor. The voltage on the inductor is the current through the inductor times the impedance of the inductor, and since the inductor and resistor are in series, they have the same current as each other, which is the same as the total current in the circuit. We'll then be able to find the peak voltage on the inductor using the peak value of the total current along with the inductor's impedance that we previously calculated to be 2309 ohms. The result is a peak voltage of 5.00 volts. Finally, for the phase of the voltage on the inductor, we recognize that because we multiplied the previous two terms, we should add the phase of the total current to the phase of the impedance of the inductor. All inductors have a phase of positive 90 degrees, and so the phase of the voltage on the inductor will be plus 60 degrees. As promised, both the voltage and the phase on the inductor turn out to be very round numbers. For the last part of the problem, the text tells us that the figure on the next page shows a plot of 1/2 cycle of the voltage from the AC power source, which we notice has a peak of 10 volts as given in the problem. We are then to sketch a half cycle of the voltage on the inductor, and we must make sure that the voltage on the inductor has the correct peak value and should be drawn with the correct phase. Let's move on to the drawing. To facilitate drawing the result, we're going to begin by sketching a line on top of the curve that is shown, and then we'll use the graphics tools in order to shrink the line to the appropriate size. We know that the voltage on the inductor has a peak value of 5 volts, and therefore we hope to shrink this curve until such time as the width is the usual, meaning that the period is the same as always, but that the height is now only 5 volts. And here we seem to have roughly succeeded at that task. Our question at this point is how we shall move this peak, because it is not in phase with the power supply, it is off by 60 degrees. The question is whether we should move it 60 degrees to the left or whether we should move it 60 degrees to the right. One of those two answers is correct, and we need to deduce the right one. in order to make the deduction correct, we're actually going to begin not by examining the voltage on the inductor, but instead making another curve that is to represent the current through the circuit. As we remember, the phase of the total current was equal to negative 30 degrees. The circuit that we have here is a combination of a resistor and an inductor. If omega L was very, very small, the circuit would basically act like a resistor, and the voltage and current would all be in phase. If omega L was very, very large, then it would act like an inductor. And the action of an inductor, as you'll remember, is to oppose changes in current. For this reason, the inductor will first set up a voltage so as to oppose the change in current and then allow it. This means that all inductors can be described as voltage first, then current. This principle will allow us to set all of these curves in place. The voltage of the power supply can't move, but since the circuit overall is partly like an inductor and partly like a resistor, it will still be voltage first, then current, but the current is only shifted behind by 30 degrees. Now we can understand what's happening to the voltage on the inductor itself. On any inductor, the voltage on that inductor precedes the current through that inductor by a total of 90 degrees. So, the full story of this circuit is as follows. Power supply generates some voltage with some phase. Because the circuit is partly inductive and partly resistive, the current is behind the voltage, but not quite by 90 degrees, only by 30. However, looking only at the voltage on the inductor, the voltage of the inductor alone is ahead of its current by 90 degrees, meaning that it is a total of 60 degrees ahead of the power supply. And this completes our analysis of phase.